I'm working at University Charles III in Madrid, and I'm finalizing my PhD thesis, so in 2 months, hopefully, I'll be a doctor. And my presentation will be like what is happening behind the simulation that we have. Thanks to Sophie and George for showing these results so nicely. I'm going to present what is happening behind the scene. What is the algorithm to generate these trajectories? I'll be presenting the framework that we are using, which is basically an aircraft trajectory planning algorithm that we developed specifically for RefMap project. And we are delivering the climate optimal trajectories, which are operationally managed. So to just give a bit of motivation of why we are doing this stuff, is that we need to consider the climate impact. Basically in the year 2024, the annual average temperature has exceeded 1.5 degrees Celsius, above pre-industrial level. Well, this is not just a simple number. It's widely considered as the tipping point, which kind of signaling the climate crisis. So we have to consider this. All sectors have to move forward and take action. Aviation specifically is one of the contributors to this warming through the emission of carbon dioxide and other non-CO2 effects, such as, for example, contrails. And as the global aviation is growing really fast, we have to take action and do immediate and perform some or suggest some immediate solution to reduce at least the climate impact of aviation. For the CO2 effects, which are well known, we have different mitigation strategies, for example, alternative fuels such as sustainable aviation fuel or hydrogen power or technological advancement. But the issue with these technology is that they are medium to long-term measures. So we need also to consider short-term measures. The non-CO2 effect, which has been claimed to be even 2 times higher than CO2 effect, are highly depends on the time and location of the emission. So basically, it is possible to identify specific areas of the aerospace and try to reroute these areas or intentionally fly through them if they have cooling impact to reduce the overall climate impact. The good thing about this strategy is that they are feasible with existing infrastructure and they are relatively immediate solution. So we just need to reroute the trajectories. We don't need to change any engine or the aircraft type or anything. But the issue with this approach of rerouting flight trajectories is that is it really operationally possible to adopt this trajectory? How this rerouting can affect the overall performance of the traffic. Here for illustration, we bring 2 different sets of traffic. This is a traffic over Spain, the Spanish airspace. Here you can see the business as usual trajectories, and here you can see the climate optimized trajectory. And these light areas show the warming area, which we need to avoid. As you can see, when we consider this area, the aircraft try to avoid this area, like this warming area. Instead, they fly through neighboring areas or in some cases that we have cooling, through cooling areas. If we adopt this trajectory in real operation, we will redistribute traffic pattern. For example, you can see that here we will have an increase in the traffic flow, which can adversely affect the overall performance. It may cause safety issues, for example, in this area, or it may increase the workload of the air traffic management to manage these trajectories. So it's not that we only consider climate impact. We also need to consider if this trajectory can be really flight in the real operation. So far, like here we have listed the most recent study on climate optimal flight planning. you can see that most of them have considered micro-scale trajectory planning, meaning that they just report the value that we can gain from deviating from the shortest path to reduce the climate impact based on individual flight, just single flight. But no one has addressed the impact of this trajectory on the overall performance of the ATM system, or no one has assessed the safety of these routing options. So, in the RefMap project, for the first time, we are addressing this issue to address both climate impact and the complexity or safety of the traffic. So, the main objective of this work package, or the work that we are doing within the RefMap project, is to first mitigate the climate impact, then try to maintain the traffic manageable, or it should be basically safe or comparable to business as usual trajectory. We have different indicators to assess the manageability of the traffic. In this project, we have considered complexity as the level of difficulty of managing a specific kind of trajectories. For example, here you can see two different traffic sets. This one is a complex traffic and this is an organized traffic. So within this project, we are trying to generate or develop trajectories which can be easily managed. And also we have to consider the operational cost, because in the end, the stakeholder may refuse to adopt this trajectory because they may have like a huge cost. So basically, we are looking for the solution which fall within the intersection of these main objectives to address both manageability, climate impact, and operational cost. So how we address this problem? What is the optimization or the algorithm behind the platform that the Sorties group showing? Basically, we are here developing or proposing an optimization module which take business as usual trajectory and weather data and produce optimized trajectory which address all the considered objectives within the RefMap project. So, how we mathematically address this problem? For mitigating the climate impact, mathematically speaking, we identify climate hotspot area, for example, these areas, and try to modify aircraft trajectories to avoid this area. They will be considered as constant in the optimization framework. And to maintain the manageability of the traffic, we consider the complexity of the traffic and consider it as the objective function, which would be minimized. Then we can claim that these kind of trajectories which address these two objectives would be ideal solutions. So solving this problem is not really simple. We have, for example, a specific case that was showing on the platform. We have near 6,000 flights. Each of them has a complex dynamical system. They have interaction. For example, for complexity, we have coupling objectives. So it's not that we can reroute one flight or consider the complexity for one flight. We have to consider the interaction of all these flights. So the solution that we propose is to use constraint multi-agent reinforcement learning. Basically, constraint multi-agent reinforcement learning can be formally modeled as a constraint Markov decision process. Within this framework, we consider different agents. Each of them have an observation from the environment and take action according to this environment. And then, when they apply the action, they will receive some rewards which show how good their action was, and some safety or some penalty constraint. Basically, it is a kind of try and error process to find the optimal policy for each of the agents that maximize the reward, which is desired and we want to maximize it, and avoid some safety or constraint. How we use this framework for optimizing aircraft trajectories to address the objectives that previously presented. We consider each aircraft in the aerospace to be an agent. they will receive information about the trajectory data, hotspot information, for example, and the information of the neighboring, because in the end, they want to also ensure safety. And take some action. For example, they can deviate from lateral path, or they can change the altitude, or they can change their speed. When these actions generated by trajectory are applied to the environment, which is the aerospace, the shared aerospace that all the aircraft are operating at the same time, we will receive a reward, which is the amount of the complexity that we could successfully mitigate. And they will have a cost penalty, which would be the cost of crossing the hotspot area. If we cross the hotspot area, then they will definitely have a cost. If no, then it's going to be the perfect solution. I'm not going to go to the mathematical part of this algorithm in more detail, but to show how this algorithm works, we tried this algorithm using a case study on December 2018, the same scenario that was presenting on the platform. From 12 to 14 in the afternoon. And we use the data source, which is the DDR2 data source, for those who are interested. And also we use the reanalysis data set for the weather data. And here you can see the map of the trajectories. These are the trajectories shown with the flight level. And here you can see the performance of the algorithm, which the gray shows the business as usual trajectory performance, and the green one shows the optimized trajectory that we deliver. You can see that by using this framework, we can reduce the contrail climate impact by 79%. But we can also reduce the complexity with respect to business as usual trajectories. So we can kind of claim that we deliver trajectories which do not disturb the air traffic management system. And we assess the operational cost. All these advantages definitely should be defined or should be delivered at a specific cost, which here would be 0.8% increase in the operational cost. And here maybe the map is repetitive of the platform, but just to show and have an overall view of how like the climate impact look like or the complexity. Here we show these trajectories are initial or business as usual trajectories. Here we can see the climate impact. The blue colors show the cooling impact, and the yellow and red the warming impact. And here the map of the complexity. So ideally we are going to mitigate these warming impacts and try to keep the complexity similar to this level. And here you can see that the performance of the trajectories that we deliver within the RoughMap project. We can see that we successfully reduce like the climate impact, warming impact, and with the same level of complexity. Even in some areas, we reduce, for example, here the complexity. So we can claim that the trajectories that we are delivering, the aircraft trajectories that we are delivering within the RoughMap project are operationally feasible. So just to give a conclusion is that we cannot just reroute trajectories and say that we reduce the climate impact. We have to consider the operational performance and the complexity of the traffic. And within the RoughMap, we propose a framework using advanced multi-agent reinforcement learning to address this specific problem with promising results when assessed for the real traffic situation. Thank you all for your attention.
We can accept one question. Just you. Just you.
Thank you for presenting that. One quick question. Keeping aside the direct operating costs of an operator for rerouting to avoid, let's say, a climate hotspot, is there scientific data that supports what, for example, 15 minutes or 20 minutes of extra flight time to avoid a hotspot, what that impact versus flying through the hotspot will have in the overall? What I'm trying to get at is there cases where the climate impact is actually better to fly through the hotspot than to reroute for an extra 20 minutes of flight time, thereby creating additional emissions than normally you would by going direct to the location.
Yes.
Is that considered in the model?
Yes, kind of. It's being considered. As you, for example, can see in some areas, we could not really avoid all the warming countries. Like, for example, in some cases, we have some warming impact, which due to the increase, like extremely increased operational costs, we have to not deviate. We decide to fly through some area because it's so costly that we cannot avoid them. So it's kind of specifically considered in this model.
Keeping cost aside, so we're not looking at the operating costs, we're going an extra 2 hours of flight time. Is there data that says flying through a hotspot versus additional emission is an extra, 10 minutes of flight time, there's more emissions, right? Which is maybe not in a hotspot, but it's more emissions. Is that modeled in there as well, the comparison,
Yes.
the climate index comparison?
Actually, the cost is not only flight time, it's also fuel consumption,
Right.
which the emission is kind of implicitly inside the fuel consumption.
Okay.
And also regarding, for example, the climate impact, which we say that we reduce, for example, for NOx emission or for CO2 emission, for their climate impact, they are directly depend on the fuel consumption or the amount of emission. So if we say that we reduce the climate impact, it means that we kind of implicitly consider the emission in the model.
Related to that, do you have also to account the financial cost of CO2 emissions? Because you do a lot of savings, so that is coming in place.
I don't think that we specifically consider financial cost. I mean, what do you mean by financial cost?
Cost of fuel.
Yeah, cost of
Not
fuel,
cost
yes.
of fuel, but also the emission and carbon credits.
You pay it.
No, but
not
we
clear.
didn't explicitly consider this cost, but as I said, it's implicitly included in the model because for the climate impact, we also consider the impact of CO2, which is which if we reduce the climate impact, we can kind of claim that we reduce the CO2.